Hey there YouTube, Paul here from the engineeringmindset.com. In this video we're going to be looking at the basic HVAC system, and this is an essential part of any building because it supplies the heated, ventilated and air-conditioned air to the space, and it ensures that it is the correct temperature, the correct humidity, and also the correct level of CO2, the correct freshness of air in that room to keep the occupants and maybe the equipment. Maybe it's serving some offices, maybe it's serving your home, maybe it's serving a data center, or even just a server room. And so obviously each one of these will have a different approach, needs different conditions to be kept in, and so the characteristics will change. But we're going to look at just a simple scenario for how one of these would be set out. Obviously, if you're watching this, you're probably just starting out in building services, so it's important that we start off with the more simpler systems. They can get far more complex than this, but this would be a great video just to get your understanding, your level of knowledge built up, so you can move on to those ones. So one of the main focuses we're going to be looking at is this part here, which is the AHU, or the air handling unit. It's got a slightly different name around the world, but this is the acronym which I work to. But we're going to be looking through how this works and each one of these components, what's happening inside, and how that air enters into the building, into the AHU, is conditioned, what's happening. We'll have a look at some real life examples as well of each part of that. Now, if you remember from one of the first videos I did on this channel, we looked at this kind of schematic here of how each part of the of the HVAC system is connected, and we looked at how the chiller here down in the basement, the AHU and the cooling towers, how they're all connected and what they're doing there. So we're going to be looking at this part here today, which is the AHU, the air handling unit, and that is what supplies the HVAC system, or conditioned air to the floor, or the floors, or the area within the building. So we'll focus on this part today, but just to recap your minds there, if you haven't watched the video on this system, please go back or check out the channel, and please go back and watch one of the first videos we put on there about how the chiller, cooling tower and AHUs work together. We've also got some videos on both the cooling tower and also the chiller, so you can get an understanding of that. And I'm just going to say I'm pretty pleased that some of you have spotted that this pump here is actually piped around the wrong way. So this pump should actually be connected to the riser here, or the flow pipe going up to the cooling tower of the condenser water system. Unfortunately, I made a mistake when I was rushing to put this video together, and I piped it onto here, but thank you for pointing that correction out. Just run you through this again. So here we've got the evaporator on the bottom of the chiller, and that's where the chilled or the cold water is produced. So that chilled water is then pumped up through the riser, and then enters, taps off of there, enters the floor, and then enters into the AHU, and we're going to be looking at how that gives off its coolth there. So that cold water, chilled water will be entering into a coil inside there, and the water then returns through that into the riser. The air within this space needs to be conditioned, so there's a fan inside there which we'll also be looking at, and that's going to suck the air from the office into the AHU, and that will then cool it down and may heat it, it may humidify it, and it's also going to filter it and check that there's enough fresh air in that space as well. And then that air is going to be pushed out onto the floors through the ductwork. I haven't shown the ductwork on this, but you'll see an example shortly. and that's distributed around the office. So that water there, that warm air which is returned, enters into here, gives up its heat, so it transfers the warm air, the heat from that, into the coil of cold water, and the cold water gives off its coolth into the air, so it comes out cold air here, and that obviously raises the temperature of that water, and that then returns it back to this riser into the evaporator of the chiller, where it then gives off its heat into the condenser side of the chiller. That is then pumped up. They're two separate systems, by the way. You should know this from the other videos I've done. But that heat is then sent up to the cooling towers where it's rejected, and the water then, the condensed water, drops a few degrees Celsius and then or Fahrenheit, and then returns back into the condenser there, ready to pick up more heat from the building. So we're going to go along and look at how this system now works. So let's just have a look at the model we built here. It's just a very basic model of an office floor. It can be much more complex than this. Obviously, if you're watching this, you're probably at the beginner's level and you're wanting to learn and expand your knowledge in HVAC and building services. So let's stick with a fairly simple example for now. What's happening here is we've got an area within the building known as a plant room. And within there is where all the mechanical and electrical assets are kept. So this is where all the engineers will be, and usually people who are in the offices in these areas here will never see this, and they'll have no idea that this is actually in their building and where all their power and air conditioning, etc., is all controlled from. But this is probably the area where you will be spending most of your time. As you're watching this, you're probably an engineer or a facilities manager, or in a similar sort of field. So let's just have a quick look at what this is doing. Now we've got, excuse me, if you imagine this is the outside of the building, so we've got two grills just on here, and this is just a mesh. And all that's really doing is stopping any material coming into the AHU. And I'll just show you an example there of one of these grills catching a lot of rubbish. So this was intake was positioned near the bins of the building, and if this mesh hadn't have been there, then this could have potentially been sucked into the fans. It should have been picked up by the filters on the other side, which we'll look at in a bit, but it still could have built up on the inside and caused some damage in there. So it's good to have a grill on the outside first to catch anything, stop any animals or anything getting in there, anything that could cause any damage. And it's obviously important to clean this off periodically as well. So coming back to the model, and you'll notice here that we've got the two ducts. We've got the one on the bottom here and the one on the top. So this one is acting as the supply, and this one is acting as the return of the discharge here. So here fresh air is coming in and entering into the AHU, and this one, all the dirty air, all the warm used air is being pushed out here and back into the atmosphere. It's obviously important not to have these two ducts too close together, because you'll just get recirculation. So ideally these would not be positioned so close, but for an example, and you can see how this is working, I've left it so close. But in the real world, do not do this. Don't put it as close as that. So let's go back to the AHU. Position that a bit better. So the supply air will enter into here. It's being sucked in, and there's a fan in here, and we're going to look at all these components one by one, don't worry. We'll just go through and make sure you understand what the system is doing first. So once that air has been pulled into the AHU, and it passes through here, which is the HVAC parts inside, and that then gets pushed into the ductwork, and that gets sent off around the building It could also go into a riser here, and that can go up, and that could spread to several floors. It could go down below as well. It could these could potentially be positioned on the roof, and these could be supplying all the floors below. This could be in the basement. It could be feeding all the floors above up to a certain height, or it could be in this example where you've got one AHU per floor. Maybe these are all tenanted offices, so a different company rents out each floor and they want full control of all their air conditioning, HVAC. So in this example, this is just a simple example where we've got two main offices and a private one maybe, and this is per floor. So that conditioned air is then entering, and then it channels off here into this ductwork and then comes out these grills, enters into the room. It will come and is dispersed and diffused into the room. These will be carefully positioned and designed to make sure that there's adequate flow in the room and that it's capturing the right areas, and that will carry on through all the rooms here until it's got a dead end, or it could continue to more rooms, but it will cap off at one point, and that conditioned air then enters into the space where it will be circulated around, and that will then control, it will heat up or cool down the air inside, changing the humidity as well. It will also, if you imagine this is a room full of people on computers, maybe it's a call center, there's a lot of heat being generated in there, so you've got to get rid of that. You need to supply cold air or cooler air to it. You don't want to be too cold because the staff are inside, and if you imagine someone sitting underneath here, they don't want 6°C air being dumped onto their heads. They'll get sick and they'll be off work. So you've got to maintain certain conditions, which will be agreed on in the lease of the contract as well, and also the level of fresh air in there as well. So there'll be sensors in this room measuring the amount of CO2, the temperature, etc. And then over the back here we've got another grill, and this is going to the return ductwork. You can see I've also labeled them here: supply and return. So all that air is going in, pushing into this room, circulating around, conditioning it, and then it's entering back into the return duct, and that makes its way back into the return side of the AHU. And there is also a fan in this one which is sucking that air in, and that's blowing that into the main chamber and then off. And then we'll look at it later, but there's some dampers in here, and that will control how much of that air recirculates and how much of that goes back and is rejected out of the vent here into the atmosphere. So just to show you some examples of what AHUs might look like in the real world, here's just a few examples of ones I've been working on over the years, and you'll see here this is a very small AHU. It's only supplying one room, kind of a medium-sized room, but it's got the same setup as a larger system, although this one is just recirculating the same air within the room, and there's an extract elsewhere for and supply for fresh air. But this one, it's just bringing in that return air. It's coming in, it's being filtered. You can see you've got the pressure gauge here, and we'll look at each part of this more later on as well. Then we've got the heating coil here. You can see you've got the flow there, and then it's returning. And then we continue. There's another panel, access panel here, and then it hits into the cooling coil, and that has the flow here and return going along. We've got some pressure gauges there, and then it continues through here. Looks like there's another filter here actually. We've got the pressure gauge going across there, and then inside this part here will be the fan, which is sucking all this air in and pushing it through, and that then pushes that air up back to the space. The second AHU which you're going to look at, This is slightly different. It's only got a cooling coil on it, so the air's coming in here and it's being sent off again, off into the space. But you'll notice that this one has got some VFDs on it, some VSDs, variable speed drives or variable frequency drive, and they control the speed of the induction motor, which is connected to the fan. And the fan is obviously pushing that, so if you change the speed of the induction motor, if you change the frequency that it's operating at, from 50 or 60 hertz down to 40 hertz maybe, then you'll slow the revolutions of the induction motor down, and that's directly connected to the fan, or maybe not directly coupled. It might be on a belt drive, etc. But you can change the flow volume of air into the space through these here. You'll also see these isolators here, so you can cut the power off to whatever they're feeding. So these two here will be directly feeding the fan as well, or the motor. And the final example, this one, this has got the flow and return on top of each other, but you might notice that this has got two heating coils on it, and also that the air on this one actually comes in and transfers. This is fresh coming in and is supplied here, and then the return is coming in and it crosses over down here, out and away. This is a much more complex version, which we'll look at in future videos. Right now you don't really need to understand that, but I just thought I'd show you some examples of what AHUs will look like in the real world. Now, to open up the AHU, you're going to need to open some of the panels up, the access panels, which are purposely there for that exact reason, so you can climb inside and have a look or fix or change the filters, change the belts, etc. So on the AHUs, on the panels you can access, you'll see these handles here. You might have handles, or it might just be a panel key fitting. In this instance here, they've got the panel keys there, so you would undo these and just lift those off, and in this case you would just turn these and that will undo the hook, and that will allow the entire panel to come off. It's obviously important to switch off any fan that's inside here first, cut the power, because it's obviously very dangerous, and you might get sucked in and potentially lose an arm or a finger or something, so please make sure you was to do that. And you can use a panel key like this just to gain access and open up and have a look inside the AHU. And while we're on that point, I'm just going to actually take the sides, the panels off of this AHU, just so you can look inside. I'll just show you built some little doors there so you could look inside like a real one. In this one that's got the filters, but we'll look in these. And just to make it clearer and easier for everyone, I'm just going to take these panels off. So I've taken the sides off of this AHU, and now you can see what's some of the components are inside. And remember, we've got the supply side down the bottom here and the return side at the top here. And from this you can see it's a fairly typical example of a typical office supply, and that is that we've got the supply coming in. It's coming in through the grills, then past the dampers. It's coming in, it's got the panel filters here, then the bag filters, then it's passing through these coils. In this configuration I've done it that heating is first and then cooling. You may have it just heating, you may have it just cooling, you may have cooling before, and you might have some humidifiers, etc. in there. But this is fairly typical, at least for the UK and most of Europe. And then we've got the supply fan here, which is pushing that conditioned air off and into the ductwork to go around and feed the floors, where it's brought back through this ductwork here, being sucked by this fan again, driven by this induction motor, and that's pushing that air into here. And then when it gets to here, the controls of the BMS system is going to decide how much of that air being drawn out will be sent back outside, and how much will be sent back into the building. And there is a reason for that. Now, you don't have to have this here. You could have that duct straight across and this also duct straight across, so that these two are not connected. Now, and that's certainly the way in the past it was achieved, but it's really expensive to do that. So if you imagine, if you didn't have this connection here, then all that air that you brought in would have to be filtered, heated, and then cooled. And then you've spent all that money in the heating and the cooling. Remember the cooling is coming from that chiller, and the chiller costs a lot of money to actually produce that cold water, and also just to maintain all the system and have a good maintenance regime for it. And you've also got a very similar system on the heating side, and that's coming from the boiler, and that's the hot water is then coming up through the riser and entering into this heating coil first as well. And so you spent a lot of money on that, and it's gone through and around the office, etc. And that air will then be collected, and if this wasn't here, that would just send that straight back out to atmosphere. So all that conditioned air, not all of it will have been of use, and that would have been pushed straight back out. So by having these damper arrangements here, you can divert some of that back in. And it will usually depend on outside air conditions for one, and also the level of CO2 in the room or in the return duct here. And if the conditions are right, then it will channel some of that back in, and that means that the heating coil will not need to do as much work, or maybe the cooling coil, maybe the humidifier will not need to work. So you will save money by returning some of that air back into the system. Obviously there will be some fresh air. It's usually about 10% of all the air coming in the going around the system has to be fresh, but there will be some set points in the BMS, the building management system, which will control all that, and the controls experts will set that all up. But we will look at some real examples of this. Not in this video. In this one, obviously, we're just covering what's happening inside the AHU. So one of the first points I'm picking up there, and drumming on a bit, is these dampers here. Let's just look at that from a better perspective. So we've got the dampers here, and these will all be connected via controls. I've, in this example, just mechanically interlocked them, so that as we open them, they will all begin to close. So if this was at 100% open, then that means it's 100% fresh air coming in, and that's going off into the AHU, and that also means that 100% of all the extract air is being pushed back outside, because these dampers are now closed. But say the conditions are met and the temperature of the air coming back is satisfactory, and we can reuse some of this. The CO2 in the room isn't too high, so we can start to then close this, and let's bring it to about maybe 60% or something, and that will allow, if this is 60%, then this is 40%, so that's going to allow 40% of the air going in will have already been around the office, and 60% of the air coming in is fresh air. So that's coming in, and they're mixing here. That's coming in, and that's going this way. So that's that air, the cold air and the warm return air is mixing here, and then it's being pushed off and out into the building. And this is just a photo of one of the control units for the dampers on an AHU. And so this is being sent controls a signal to tell this to change its position, and that's a small motor inside which is going to turn this, and that causes these rods to rise and fall either way, and that will change. If you imagine, this can change the position of this rod here, and on the inside of the duct is the damper. And I'll just show you a real example here of that controls unit connected to the dampers. And inside there, these are the dampers inside the actual unit. And I'll just adjust the rod manually myself, and that will change the position of them. And that will allow it to open and close. There you go, you can see the mechanism there. And that changes the amount of air coming in. Okay, so the next part we're going to look at is the filters, which are in these two components here, or compartments here. Now you'll notice there are two different types of filters. This one here is known as a panel filter, and this one here is known as a bag filter. We can just pull that out and have a look at it. So the panel filter is pleated, and it goes across, and it's got this very thin cardboard on it around outside, just to give it a bit of sturdiness, and there's a wire frame inside. And so this is your first line of kind of defense to filter your air. And there is a surprising amount of dirt and just muck that comes in with the air, and you want to get rid of that and filter it out before it hits the coils, and also before it goes into your fan, is sucked in by the motor for the cooling, and is also pushed out onto the floors for the occupants, for the tenants, the office workers. They're going to be breathing this air in, so it's important that that air is cleaned and is conditioned in a correct manner. So the first line it will go through is the panel filter, and I'll just show you what a real one looks like. So this is a real panel filter taken out of the AHU. This is clean, this is brand new, ready to go in, and you can see the colour. The colour is really this kind of green colour, more to the manufacturer, and the frame here. And just to give you an example here of how that would look inside the AHU in real life. So we've got 4 panel filters of different sizes, obviously, slightly different design here by a different manufacturer, and also the material that is used, the thickness or the thickness of this filter material is what's going to capture the most dirt and germs, etc., that's going through there. And the AHU designer, and you can even bring filter specialists in, and they will advise you what filter material you should use. There's some standards which you can look up and read as well. But these filters will become blocked over time as the more and more air that passes through there. These filters will pick up all that dirt, and it will get to a point where the pressure drop across the filter becomes huge, because the fan is trying to pull all this air through, and it's blocked by this. Let me just give you an example. So this is what a clean filter looks like. You can see the metal frame there, and the filter material wrapped around it. Looks quite nice. And then a few months later, after maybe a few days, it depends where your building is. If it's sucking air off of the motorway, next to an industrial site, or maybe near a coal power station or something, you're going to be going for a lot of filters. So this is what the dirty filter looks like, only after a few weeks, a few months. It depends where you are, like I said. And you can see, look at the amount of dirt here. So this is just pollen, this is bits of skin, this is dirt, this is where cars drive along the roads and they give off all the CO2, and their tires degrade and all that rubber comes off. This is all coming in, this is all collected on here. So this is why it's important that you have filters on your airstreams, and that you clean these regularly. Just to make sure that is not entering your building, into your equipment, and also that the occupants inside are not breathing this in. You'll also find some information on the side of most of the panels, so you can see the size there. You've got the product description and the company who makes it, but you've got the size of the filter there. This one's in inches, who the customer is. I've just edited that quickly. But more importantly, you've got the direction of airflow, so you know how to install that within the AHU, how to slide that in so that the air will be passing through this way and out off into the supply duct. It's important to get that round the right way. And just to show you a filter here, this is obviously a new one. Just show you the thickness of these and the materials they use, so you can see straight through it. The light passes through. It's very thin. It changes in density, but yeah, it's very thin material. The thicker the material, the more you will capture, but then the higher your fans will have to work, so the more you spend in electricity. The second line of defense there is your panel, your bag filters even, and these usually kind of these jagged edges, so the bags go back a certain distance, and they will change that. And that changes, if you imagine, the surface area that it can capture. So it comes along there, and these can slide in and out. And a real bag filter installation will look something like this. In this example, you've got the panel filters almost directly coupled to the bag filters there. And if you imagine the air is coming through these really kind of inflate as they add resistance to the flow of air, and these will start to clean and capture all that the dirt out of the air, which we saw earlier. And here's one of the bag filters we just got out of one of the boxes, just to show you the sort of material it's made out of and its construction. You see these bags going back to capture all that air. So this is how they look like inside the AHU. You can just move there, they're very light, and you can just slide them out like this also. Sometimes they'll just have these clips here, so you can't slide them out. You just rotate these and you can just pull the clips off, take the panels out by rotating these. One way to monitor how dirty the filters are becoming is to install these pressure differential sensors onto the sides on the panels. This is just a manual reading, so you can see here it's reading in pascals on the bottom, and an inch of water along the top. And this will change as the pressure increases across there, so there's no pressure drop at the moment, but as this goes down, as the filter becomes more and more dirty, it becomes greater and greater. And so this is measuring the difference between the intake and the suction side of the across the filter, and that's how you know how dirty it is. A really good tip is to actually mark these, so put a sticker or draw a pen or something to display what a clean filter mark should be and where a dirty filter mark should be, and that way when you do your walk rounds, when your maintenance team does the walk rounds, you can go along and if it's dropped below, say it was at 150 pascals, if it's gone down to 200, the red dye, then you'll know that you should have changed the panel or the filters by now, and then you can get the maintenance regime in place to do that. You can also automate this, and if you've got the capability of a BMS system on site, a building management system, which is a computer controlled version of your maintenance guys, then this will all be built into the system, and it will give you an alarm, and you can monitor and then also do some analysis on that data as well. So this is a digital reader here, and you can see the supply side is being read through the pipe there, or the tube, and then this tube is going around to the other side of the filters, and it's just a hollow tube really, which is going to suck that in, and it will take the pressure reading across that. It's a slightly different type, and that is just basically taking the pressure reading across the filters, and it will send an alarm, an alert to the BMS that the filters are ready to be changed because the pressure drop has increased too much, and indicating that it is dirty. Now the next point we've got here is the coils. So we've got the heating and cooling coil in this configuration. The AHUs you'll come across in industry may be slightly different to this. They might, like I said, only have a heating or just a cooling. They may have a humidifier in place, etc. So, but for this example, we're just going to look at having a heating and a cooling coil there. So with your heating and cooling coils, obviously the heating one is going to be connected to your boiler or your heating system. It could also be electric. It could be an electrical heater in here, certainly for frost protection that's sometimes used. And on the cooling coil here, this is what's going to be connected to your chiller or your chilled water system. And if you remember back to the beginning of the video, that's what's coming off that riser, that chilled water coming in and passing through. And it's good to have this connected so that the flow, the coldest water is coming in and the hottest water coming in, and it's entering through the base of the coil and passing through. You'll get much greater efficiency out of this because it's going against the force of gravity, so it gives it a little bit extra time just to give off its heat. If you configure it the other way, then it's got that extra momentum of gravity, so it will pass through there and not all of it will give up all of its heat. But this is maybe a step, advanced step, and we don't need to worry so much about it yet. Let's have a look at how the cooling and heating coils work. So if I change the view here, apologies, it's going slightly boxed as my RAM is starting to run out on this computer at the moment. But as you should be able to see here, the coil is configured so the pipe inside here runs in this configuration all the way around until it, well, in fact it runs the other way, but same difference, until it exits. So the pipe is going all the way through there, and that contains, inside there is the heated or cooled water, and maybe steam. You could have steam on the hot side as well, on the heating coil. And between there are all these fins. Now these fins are usually something like aluminium, and they're incredibly thin. They really are very fine sheets of metal. Very delicate as well. If you knock them, it will dent them and it will damage them. You can get some combs to bring those out as well. But the fins, the purpose of these is that the heat or the cool inside these, if it was the air just rushing over the pipes, then it would only have the surface area of that pipe. If you imagine the air coming in here and hitting that pipe, it will go around and continue, and it's only going to take the heat or the cool off of that surface there. You'll also have these large gaps here where the pipe, there is no pipe, and so the air will just pass straight through and will not touch that. So to improve the heat transfer of this heating or cooling coil, we put these fins all the way across the pipes, and that allows the heat in there to transfer and conduct through these thin sheets of aluminium, maybe stainless steel or something, but that travels across, and that allows that air that's passing through to capture that heating or cooling energy, thermal energy, off of these fins and bring that away. So you'll get better control and better conditions. You'll be able to reach your heating or cooling set points through the use of this. So just to show you an example of how a real heating or cooling coil will look, here we've got the connections coming in, and it's just entering there, and you can see these coils are just coming around like that. The tubes are a lot thinner than the ones that I put in the model. Obviously that is just for explanation purposes, to get build your understanding. It's a lot easier to visualize it that way. So these very thin tubes actually pass all the way around, and you can see these really thin sheets of aluminium or stainless steel running through there like so. So there's another real life example of one of the AHUs, and we can just look in there through the viewing window, and you can see there just how thin these are. They're very closely packed together. This one's actually a bit dirty. They do need to be cleaned periodically, especially if it's the cooling coil, because the air will condense onto this and that will make it wet, and that means that if your filters are not capturing everything, that dirt and dust in the air will actually stick to that, so you will get dirty coils, and you'll clean it every so often. This is a heating coil, and we can just see there the flow coming down here, entering into the coil, and again you can see just how thin these coils are. You can see a few dents there as well. This has been damaged slightly during the maintenance. You can see the coils coming through there as well. Yeah. And the cooling coils might also be provided cooled by a refrigerant system, and they're all going to look something like this. These are just the thermal expansion valves there, running down with the thermal bulb down at the bottom here, and these are just running into the coil on the inside. And the coil on that one will look a bit like this, with the branches coming in and separating off. There's a few fins on this one instead, but just coming back there, there you can see the refrigerant lines coming in and splitting off and going to each of the coils that are coming and looping around there. Now underneath the coils you're probably going to find that there is a drain and some drain lines coming out. I haven't drawn it on this example here, but I will show you what they look like in the real world. So they're going to look a bit like this, with the drains coming out. You go into a U-bend there to stop the flow coming back, and that just comes down this pipe, which is on an incline, and heads down to the drain. Looks like this one hasn't been installed too well, as most of it that's going over the floor rather than down the drain, but it was a good attempt, I guess. And here's another example. So in the base of the AHU, you've got this drain here, and that will just collect up all the moisture that comes away from that. And in the peak of summer, that can actually be quite a flow rate, where all the water is condensing out of the air, and that is then channeled and goes off back to drain. Okay, so next we're going to look at the driving force of the air that's being pushed around, sucked in and pushed around the system and then rejected, and that is of course the fan units here. Now this one here, I've actually brought the fans just outside the casing, just so you can see that. And in fact, let's change that position just there a bit. There we go. No, let's rotate that a little bit. There we go. That's a bit better. So you can see here we've got an induction motor, and that's bolted down usually to a frame, because these are pre-built systems, and that's going off to the pulley, and then this is put onto a belt drive. And the end of the belt, this is kind of a rubber wire frame mesh belt, and that goes off to another pulley which is connected to the fan blades inside here. You'll notice that this fan here has backwards curved fans. There are a lot of different designs you can have. This is fairly efficient. There's a new type of fan out which is actually much more efficient than this, but I like this one just because you can really visualize what's happening there. And I have coupled these so that we can actually, as we rotate the motor, you'll see there that rotation is being transferred through the belt. The belt is then driving that pulley, and the pulley is then driving the fan there, driving the fan blades. So as that spins, and it goes faster and faster and faster, and that draws that air. All that air is being traveling along the duct there, and it's being sucked into these sides here, on the back and the front as well. So as that induction motor there and the pulley spins, it pulls all the air in, and that starts to fill this void. The back of this one is obviously pushing that air. It's coming around, and as it's doing that, it's kind of being flung off the side here. You imagine like a centrifugal force. If you spin something, it wants to go out. So as this occurs, it's following along the curve and it's being shot off, and this is pushing it, and as that comes around to say here, it's at full swing, and it gets thrown out, and there's more air coming around this way. It's being pushed, as that builds up the pressure, the static pressure in this duct here, and that drives all that air out. So that pressure difference caused there, so this will be a negative pressure or a lower pressure, and then this will be a higher pressure because it's the air here is being compressed into this duct here, and this is being sucked in, so it's a lower pressure going in. Now I mentioned the belt drive there. These belts also need to be replaced periodically. They will break, and they will wear down. In fact, I've got an example here. So this is a broken V-belt used on one of the AHUs, and you can see there it's just completely snapped, and this has had to be replaced. If you've got the good control system in the on the BMS system, it will pick up that sudden loss, that snap, and it will act on that, and it will stop the motor from running. Obviously, you should have a good maintenance regime in place to plan preventative maintenance to actually stop this occurring, but it will happen from time to time. Now, this is what a real induction motor and fan looks like. This is pretty much what I've based mine on. You can see the design is slightly different, but I've made it for illustration purposes for our one. And here you can see you've got the power supply coming into the induction motor. This cable may go off, and that may come out there, or be fed by one of these variable frequency drives, or variable speed drives, which we talked about earlier, and that controls the speed of the induction motor, and obviously they're going to the isolator, and that can be manually controlled, but it should be in auto mode. You'll see on the panel there. Maybe we'll do another video on that actually. And that goes also to the BMS, so everything's automated and can respond in real time. And so that's the power unit there, and then this is the pulley here. This is the drive shaft, which is being spun by these the magnetic field inside this induction motor, and that's rotating these pulleys and driving this pulley here, which is directly coupled here to the fan blades inside this fan here, and that's where the air is being sucked in here, and then it's being pushed into the duct and then off into the space. Here's that fan in a video here, just so you can see it in kind of real life. There we go. We got the fan there. You also get these data plates on there, and you can just see the top of the pulley there as well. There's also a data plate on top of the motor there as well, and that will tell you the kilowatts, the amps, etc. that's going on there. Now the return fan works very similar to the supplier one, just in reverse, so it's sucking the air out of there. I've just again done a simple explanation here of how that would work. So once the air has been brought into the building, it's came in, it's passed through these dampers, and it's controlled the amount of fresh air that can be brought into the space, and it's come in. The BMS has decided how much air can be reused there and recirculated. You could also put this on a manual system and change it seasonally if you don't have a BMS, or if the BMS for some reason isn't working, but obviously the more you can automate, the better the controls will be, and that will then bring that in, and then you need to filter that. Here we've got two layers of kind of filtration protection. Then we're going to go through, we're going to heat the air up and cool it down, or heat it or cool it, etc. Maybe change that to change the psychrometric properties of the air. And then what's been pulling all that air this whole time is this fan there, and that then drives this and sends it off into the space, into the offices, where the air is then dumped. It conditions the space inside the building, keeps all the occupants happy, and then returns back here through this way. Now, a schematical drawing of how an AHU will look is something like this. So in this example, the air is flowing in this way, and it's got through the filters, and the fan is pulling that in. You've got the bag filters there, and then it passes into the heating coil. You can see that because it's a plus, because it's adding energy into that stream of air. Next, it will pass directly into the cooling coil, and you see that because it's got the negative, because it's taking energy out of that system. And finally here we've got another point, which is the humidifier. Something I didn't include in my one. They're not in every AHU, but this one has got a humidifier. Looks like it's a steam one because we've got a meter there as well, and it's going through. It could also be water, but let's have a look. So this is a humidifier here, so it's got water coming in and it's just spraying this out. These small induction motors here are just spraying that water out in a very, very fine mist, and as that sprays out and it creates the mist, and that then goes off, and that's what adds humidity to the air, increases the water content of the air. Another way to do it would be through something like this, which is an evaporative humidifier. You can go for a steam system as well, so there's many ways you can actually do that, just to add moisture to the air, and it depends on the critical environment, or the environment, if it's critical or not. It used to be in many offices. This would put it in there to control the kind of the static in the air. But more and more this is being switched off. It's very energy intensive, so it's being switched off, and there's various guidelines to tell you where and when you can and can't do that, and so I would recommend you research that before switching these off. Now, I've talked a lot about the BMS system, the building management system, and this is just a screenshot from a typical BMS system of actually what the system we drew, what I had looked at earlier, the one I've made a model of. And so this is what it might look like on the computer screen. There'll probably be a bunch more readings around here. I've actually taken some of these out just to clean it up and let you see what it might be measuring. So here again we've got the dampers in their position, so it's measuring these. We've got a measurement here for the outside enthalpy. We've also got the mixed air temperature here, the fresh air velocity coming in. So you can measure how many, here it is, meters per second are coming in. If you know the size of the ductwork, then you can obviously calculate the volume flow rate coming in. Here we've got the mixed air temperature. So this will be different from the outside air temperature. You usually have another temperature sensor here, just showing you what the temperature outside is, and that would coming in. Then we're going through the panel filter, which we can see here is clean. There's no pressure drop across it, but also the fans are not on, so that wouldn't really pressure drop anyway. Then we've got the bag filter here. Next we've got a frost sensor here. So this is a temperature sensor, and that's detecting if the air coming in is probably around 5 degrees Celsius. That's the typical kind of alarm setting. So if it drops below that, then this heating valve here will open, and that will heat the air. It will supply heat to it. So here is a frost temperature sensor. You can see there it's set at 5 degrees. So if the temperature gets to that point, it will kick this on. This is an electrical one, so it's just going to add heat the electrical elements inside, and that will warm that air up in there and bring it above 5 degrees. Because if it got too cold and it hit the pipes, that could cause the pipes within the coils to burst, and obviously you'll leak that fluid into the air, and you don't want that to happen. So you've got some protection here, and then that comes off and goes into the cooling coil, and you can cool the air down here or change the humidity using this one. And then that's being sucked obviously by the fan and being pushed off. Here you can see that it's measuring the supply air relative humidity. So we've got some measurements here for the temperature and also the humidity, and it's also measuring the enthalpy here. So this is a more advanced control system, which we won't talk about so much in this video. We've got a pressure sensor here. This is reading minus figures, but the fans aren't on at the moment. Probably some calibration anyway. And we've also got some run hours here for the fans, so you know how long they've been running for, and then you can do your proper maintenance and also do some energy analysis, etc. And know your time value of money for your plant equipment, so you know that every X amount of hours these fans will need to be replaced or maintenance will be carried out of them. So it's a very good idea with BMS to log these. If you're doing it manually, then you have to guess, so you might not get value for money like that. This is the calculated supply air temperatures and the set points as well. So this is what the air will try, this system will try to achieve. So the air coming in is going to be these set points here. Again, on the extract, we've got the extract air temperature and relative humidity there, and also the temperature, and that is the extract enthalpy, the amount of energy being drawn out of the space there. And then again, that is pushed either straight out of the exhaust air, or it is mixed back round to the system here. I'll just show you an example of a temperature sensor here. So this is bolted to the side of the unit, maybe onto the top of it, and these would be various ones, and there's a rod coming inside the unit there taking measurements of the temperature of the air. And you may have noticed at the top here this tube sticking out, sticking through the top. That is your temperature sensor right there, and that's taking the measurement going onto this heating coil here, and will dictate through the controls how that should operate in response to that. Okay, that's it for this video. Thank you very much for watching. I hope you enjoyed it. Please like, subscribe, and share. And if you have any questions, please leave your comments in the section below. More than happy to assist, and also give me some recommendations. What would you like to know? What would you like to see me make next? Yeah, I'd really appreciate your feedback. Obviously, we're on Facebook, Twitter, Google+. Also got a website, which is theengineeringmindset.com. You've probably seen this written out throughout the video several times.